Welcome to today's session. We will be tackling an interesting coding problem titled Self-Dividing Numbers. In this problem, we'll explore how to identify numbers within a range that meet specific divisibility criteria. Let's dive in and break it down step by step. In this problem, we are working with a concept called a self-dividing number. A self-dividing number is a number that can be evenly divided by each of its digits without leaving a remainder, and it must not contain the digit 0. For example, the number 128 qualifies as a self-dividing number because it is divisible by 1, 2, and 8. However, a number like 102 does not qualify because it contains the digit 0, which violates the rules. The task is to find all the self-dividing numbers within a given range, defined by two integers left and right. The result should be a list of all self-dividing numbers between these two boundaries, inclusive, where both the start and end numbers are part of the range. The input consists of two integers, left and right, that specify the range, and the output is a list of all qualifying numbers within that range. Let's look at an example to better understand how this works. If the input range is left equals 1 and right equals 22, the output will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 12, 15, 22. This is because single-digit numbers like 1 through 9 are always self-dividing, they are divisible by themselves, and they don't contain the digit 0. However, a number like 10 is excluded because it contains the digit 0, making it invalid. For the number 11, both digits are 1, and since 11 is divisible by 1, it qualifies. Similarly, 12 qualifies because it is divisible by both 1 and 2. Numbers like 13 or 14, though, do not qualify because they are not divisible by all their digits. For instance, 13 is not divisible by 3. This pattern continues, and we include numbers like 15 and 22 because they meet the criteria of being divisible by all their digits. Now, let's examine another example with a different range. If the input range is left equals 47 and right equals 85, the output is 48, 55, 66, 77. Let's break it down. The number 48 qualifies because it is divisible by both 4 and 8. On the other hand, 49 is excluded because it is not divisible by 9. The number 55 qualifies because it is divisible by 5 twice, as both digits are the same. Similarly, 66 qualifies because it is divisible by 6 twice. Lastly, 77 is included because it is divisible by 7 twice. Numbers like 50 or 60 are excluded because they contain the digit 0, which automatically disqualifies them. So, in this range, only 48, 55, 66, and 77 meet the criteria for being self-dividing numbers. The problem comes with some constraints and edge cases to consider. The constraints are that the range, left, right, will always be between 1 and 10,000, and both left and right are integers. Additionally, any number containing the digit 0 is automatically not self-dividing. For edge cases, if the range consists of a single number, such as left equals 15 and right equals 15, we need to check if that number itself is self-dividing. Another edge case involves ranges that include numbers with zeros, or we need to exclude those numbers. Finally, for very large ranges, such as from 1 to 10,000, the solution must be efficient and able to compute the result within a reasonable amount of time without timing out. These constraints and edge cases ensure the solution is robust and handles all possible inputs correctly. To solve the self-dividing numbers problem, the brute force approach is the most straightforward method to start with. The intuition here is to simply check every number in the given range, left, right, to see if it meets the conditions of being self-dividing. This involves breaking down each number into its individual digits and verifying two key conditions: first, that no digit is 0, and second, that the original number is divisible by each of its digits without any remainder. If either of these checks fails, the number is not self-dividing and is skipped. Otherwise, it gets added to our result list. While this approach is simple and easy to implement, its time complexity is proportional to both the number of integers in the range and the average number of digits in each number, which can add up for large inputs. However, the space complexity is minimal, requiring only constant extra space besides the result list. The trade-off here is that while it's a good starting point, it's not the most efficient solution for larger inputs or ranges with many multi-digit numbers. Now, to improve on the brute force approach, we can make some optimizations that enhance both clarity and performance. Instead of converting numbers into strings to extract their digits, we use arithmetic operations, specifically integer division and modulus, to directly work with the digits. This eliminates the overhead of string manipulation. Additionally, we can terminate the process for a number early if we encounter a zero digit or any digit that doesn't divide the number evenly. This avoids unnecessary checks once we've determined that the number cannot be self-dividing. The steps involve iterating over the range, left, right, extracting the last digit of each number using modulus, and checking if it satisfies the conditions. If it does, we remove the digit by performing integer division and continue until the number is fully processed. If all digits meet the criteria, the number is added to our result list. While the time complexity remains the same as the brute force approach, this method involves fewer operations per number, making it slightly more efficient. It also avoids the need for additional memory to handle string conversions, keeping the space complexity minimal. The optimized approach was chosen as the strategy for solving this problem because it strikes the perfect balance between simplicity and performance. It directly addresses the problem requirements without adding unnecessary complexity, making it easy to understand and implement. Given the constraints of the problem, which involve relatively small ranges and manageable inputs, there's no need for advanced techniques like parallelization or low-level optimizations. A key insight here was recognizing that string manipulation is unnecessary. By using arithmetic operations such as modulus and division, we can efficiently process each digit of a number. Another significant improvement comes from early termination, which avoids redundant checks by stopping as soon as a failure condition is met. These insights combined make the optimized approach both elegant and effective, ensuring that we solve the problem efficiently while keeping the logic clear and focused. When we compare the two approaches, we see that the brute force method has the advantage of being simple and intuitive, but it also comes with some inefficiencies. For example, it performs redundant operations, like continuing to check digits even after a condition has already failed. On the other hand, the optimized approach eliminates these redundancies by leveraging arithmetic operations and early termination, which makes it more efficient in practice. While both approaches share the same asymptotic time complexity, the optimized approach minimizes constant factors and unnecessary operations, resulting in better performance overall. In conclusion, the optimized approach is the ideal solution for this problem because it balances clarity, simplicity, and efficiency, addressing the problem requirements effectively without introducing unnecessary complexity. To solve the problem of finding self-dividing numbers, let's first define what this means. A number is self-dividing if it can be evenly divided by each of its digits without leaving a remainder. For example, the number 128 is self-dividing because it is divisible by 1, 2, and 8. The task is to identify all such numbers in a given range, left, right. A straightforward approach to tackle this is the brute force method. In this approach, we systematically examine each number in the range to determine if it fulfills the self-dividing property. To implement this, we start by creating an empty list, result, to store all valid numbers. Then, we iterate through every number in the range, left, right, using a for loop. For each number, we check whether it qualifies as self-dividing, and we'll discuss how to do that step by step. The key to identifying whether a number is self-dividing is to evaluate its digits individually. To achieve this, we define a helper function called is_self_dividing number. Within this function, we use a temporary variable, temp, to hold the current number. Using a while loop, we extract each digit by taking the remainder of temp divided by 10, which gives the last digit. Then, we check two important conditions. If the digit is 0, the number cannot be self-dividing because division by 0 is undefined, so we immediately return false. If the number is not evenly divisible by the digit, we also return false, as this violates the self-dividing property. If all digits pass these checks, the function returns true, indicating that the number is self-dividing. Back in the main loop, whenever is_self_dividing number returns true, we append the number to the result list. After processing all numbers in the range, the result list, which now contains all valid self-dividing numbers, is returned. When analyzing this algorithm, there are some key insights to consider. First, handling edge cases is crucial. For instance, any number containing the digit 0 can never be self-dividing because division by 0 is undefined. Additionally, the range, left, right, could include both very small values, like 1, which is always self-dividing, and large numbers, so the algorithm needs to work efficiently for a wide range of inputs. The process of extracting digits is done by repeatedly taking the remainder of the number divided by 10, and then reducing the number using integer division by 10. This ensures that we process each digit from right to left in an efficient manner. Another important optimization is early termination. If at any point we encounter a digit that disqualifies the number, such as a 0 or 1 that does not divide the number evenly, we immediately stop further checks and return false. This prevents unnecessary computations. Finally, constructing the result list dynamically allows us to efficiently store and return all valid self-dividing numbers at the end of the process. The algorithm relies on simple and effective data structures. At its core, we use a list called result to store all valid self-dividing numbers. This is ideal because lists can dynamically resize as we discover new numbers. Additionally, we use temporary integer variables like temp, digit, and number for arithmetic operations in digit extraction. Now, let's evaluate the algorithm's complexity. For time complexity, let's assume the range, left, right, has n numbers. For each number, we process its digits, and the number of digits is proportional to O log number. This gives an overall time complexity of O n asterisk log, max, left, right, where max, left, right, represents the largest number in the range. As for space complexity, we use O n space to store the result list, while the additional space for temporary variables is constant, making the overall space complexity O n. Now, let's see the algorithm in action with an example. Suppose the input range is left equals 1 and right equals 22. We start by iterating through every number from 1 to 22. For each number, we extract its digits one by one and check if the number is evenly divisible by each digit. If it is, we consider it a valid self-dividing number. Following this process, the self-dividing numbers in this range are 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 12, 15, 22. These are numbers that satisfy all the conditions we've discussed, including handling numbers with no zero digits and ensuring divisibility. The final output is the list 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 12, 15, 22, which is returned as the solution. This implementation solves the problem of finding self-dividing numbers in a given range. A self-dividing number is one that is divisible by each of its own digits, and no digit in the number is 0. The self-dividing numbers function takes two inputs, left and right, which define the range within which we want to find self-dividing numbers. The method defines a helper function, is _self_dividing, to determine whether a number meets the self-divisibility criterion. #### key steps. 1. Helper function, is _self_dividing checks a number digit by digit. It uses modulo, %, to extract the last digit in integer division, // to remove the last digit. If any digit is 0 or the number is not divisible by one of its digits, the function immediately returns false. Otherwise, it continues checking until all digits are processed. 2. Iterating through the range, the main function iterates through all numbers from left to right. For each number, it calls is _self_dividing. If the number is self-dividing, it is added to the result list. 3. Returning the result, after the loop completes, the function returns the result list containing all self-dividing numbers. This implementation ensures correctness by checking all digits and efficiently handles the edge case where a digit is 0, which automatically disqualifies the number. The solution is clear and concise, with a time complexity of O n*d, where n is the number of integers in the range and d is the average number of digits per integer. Here, we begin by importing the necessary libraries and defining our solution class. The main method of interest is self-dividing numbers, which takes two parameters, left and right, representing the inclusive range within which we want to find self-dividing numbers. We initialize an array list called result to store these numbers. Then, we use a for loop to iterate through each number in the range. For each number, we call the helper method is self-dividing. If this method returns true, we add the number to our result list. The helper method, is self-dividing, is designed to determine if a number meets the self-dividing condition. To do so, we store the original value of the number in a variable called original and then enter a while loop that processes each digit of the number. In the while loop, we extract the last digit of the number using the modulo operator. If the digit is 0 or the original number is not divisible by this digit, the method immediately returns false since the number cannot be self-dividing. Otherwise, we remove the last digit by performing integer division by 10 and continue the loop. If the loop completes without returning false, it means the number satisfies the self-dividing property, so we return true. Finally, in the main method, we create an instance of the solution class and call self-dividing numbers with the range 1 to 22. The result is printed to the console, showing all self-dividing numbers within this range. To solve the problem, we start with the range of numbers from 1 to 22. The goal is to identify which numbers in this range are self-dividing. We begin by iterating through each number one at a time. For the first number, which is 1, we check if it is self-dividing. The number itself is stored as original, and we start processing number. We extract the last digit, which is 1, and verify that it divides the original number evenly. Since 1 divided by 1 equals 0 with no remainder, it meets the criteria. With no more digits left to check, we conclude that 1 is self-dividing and add it to the result list. Next, we move to 2. Similar to 1, we extract the digit 2, confirm divisibility, and add it to the result. This process is repeated for all single-digit numbers from 3 to 9, and since all single-digit numbers are self-dividing by definition, we append them to the result list as well. Now we examine the number 10. For 10, we extract the first digit, which is 0. Division by 0 is not allowed, so we immediately reject 10 as a self-dividing number. Moving forward, we continue checking numbers from 11 to 22. For each number, we extract its digits one by one, ensuring that none are 0 and verifying that each divides the original number evenly. Based on this criteria, the numbers 11, 12, 15, and 22 qualify as self-dividing and are added to the result. By the end of this range, our final result list for numbers between 1 and 22 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 12, 15, 22. Next, we focus on a smaller range, from 10 to 15. We start with the number 10. Since it contains a digit 0, it is immediately disqualified. For 11, we check both digits, confirming that each divides the number evenly, so we append it to the result. Moving to 12, we verify divisibility for both digits, 1 and 2, and add it to the result as well. For 13, the last digit 3 does not evenly divide the number, so we skip it. Similarly, for 14, the digit 4 is not a divisor of the number, so it is also skipped. Finally, for 15, both digits, 1 and 5, divide the number evenly, making it a valid self-dividing number. The output for this range is 11, 12, 15. In the case of a very small range, such as 1, 1, we only need to evaluate a single number, which is 1. Since 1 is a single-digit number, and single-digit numbers are always self-dividing, we append it to the result. The output for this edge case is simply 1. Some key observations from these examples include the fact that a number can only be self-dividing if all its digits are non-zero and every digit divides the number evenly. The is_self_dividing function handles this by iterating through each digit of the number to ensure it meets these conditions. Additionally, single-digit numbers are inherently self-dividing, while numbers containing the digit 0 or any non-divisible digit are automatically excluded from the result. To understand the time complexity of this solution, we start with the outer loop. This loop iterates through every number in the range, left, right. The total number of iterations performed by this loop is determined by the size of the range, which is right, left plus 1. Now, for each number in the range, we call the is_self_dividing function to check whether the number is self-dividing. Inside this function, we extract each digit of the number using operations like modulo and integer division. The number of iterations required for this digit extraction is proportional to the number of digits in the number, which is mathematically represented as log 10 number. So, the time complexity for processing a single number within this function is O log 10 number. Now, let's combine these components to calculate the overall time complexity. For every number in the range, left, right, the is_self_dividing function is executed. Let's consider the largest number in the range, denoted as m equals right, which has the highest number of digits. In the worst case, every number in the range has the same maximum number of digits, which is log 10 m. The outer loop runs, right left plus 1, times, and for each iteration, the inner function executes in O log 10 m time. Multiplying these two factors gives us the total time complexity, O right left plus 1 asterisk log 10 m. This represents the combined cost of iterating through the range and checking each number for the self-dividing property. Next, let's analyze the space complexity of the solution. Starting with the is_self_dividing function, we see that it uses a constant amount of space to store variables like original, digit, and number. This means the auxiliary space used within the function is O1. On the other hand, we also need space to store the results of all self-dividing numbers in the range. This result is stored in a list called result, which, in the worst case, could contain all numbers from left, right. Since each integer stored in the list requires O1 memory, the total space required for the list is proportional to the size of the range, or O right left plus 1. Combining these factors, the overall space complexity of the solution is O right left plus 1, as the result list dominates the memory usage. Let's compare this approach to a brute force method and discuss best and worst case scenarios. The current solution is already optimized because it stops checking a number as soon as a non-self-dividing condition is encountered. In contrast, a brute force approach would involve testing all possible numbers without any early termination, but it would ultimately result in the same asymptotic complexity. Now, looking at specific cases, the best case scenario occurs when all numbers are small, such as single-digit numbers, which minimizes the digit extraction process inside the is_self_dividing function. Here, the time complexity remains O right left plus 1 asterisk log 10 m, but m is small. In the worst case, the range contains large numbers with the maximum number of digits, leading to the same formal time complexity of O right left plus 1 asterisk log 10 m, but with m being large. Finally, we can summarize the mathematical proof of the time and space complexities using big O notation. The outer loop executes O right left plus 1 times, iterating through every number in the range. For each of these numbers, the inner function runs in O log 10 m time, where m is the largest number in the range. Combining these factors gives the overall time complexity as O right left plus 1 asterisk log 10 m. On the space complexity side, the result list, which stores up to right left plus 1 integers, dominates the memory usage. Since each integer requires constant space, the total space complexity is O right left plus 1. This completes the analysis of the time and space complexity for this solution. When solving the self-dividing numbers problem, there are a few common mistakes to watch out for. First, forgetting to handle edge cases can be a major issue. Numbers containing the digit 0, like 10 or 20, cannot be self-dividing because division by 0 is undefined. If you don't explicitly check for 0, your program might crash or produce incorrect results. To avoid this, you should add a condition to skip any number that contains the digit 0. Next, there's a frequent misunderstanding with division checks. Some assume that integer division, such as number/digit, guarantees divisibility, but this is not the case. Instead, you must use modular arithmetic, specifically number %digit equals 0, to confirm that a digit divides the number without leaving a remainder. Lastly, inefficient iteration is another pitfall. Rechecking digits unnecessarily or using nested loops can inflate the time complexity, especially for large ranges. The solution here is to use a single loop to extract digits and validate conditions efficiently, reducing redundant computations. Another common mistake is misinterpreting the problem statement. Some confuse self-dividing numbers with concepts like numbers divisible by their sum or product of digits. This misunderstanding leads to solving a completely different problem. To avoid this, take the time to carefully read and understand the exact requirements of the problem. Additionally, off-by-one errors in handling the range, left, right, are a frequent source of bugs. Since the range is inclusive, forgetting to include either boundary can cause you to miss valid numbers. The solution is to ensure your loop covers all numbers from left to right, inclusive. Being precise and thorough with these details will help you avoid unnecessary frustration and ensure your solution meets the problem's expectations. From an interview perspective, self-dividing numbers is an excellent problem for practicing key programming concepts. The main pattern to focus on is that every digit of the number must divide it without leaving a remainder. This makes the problem a great opportunity to refine your skills in digit extraction and modular arithmetic. Optimization is another important focus area. Interviewers often appreciate solutions that minimize unnecessary work, so implementing early exits when a non-divisible digit is found can be a strong strategy. Additionally, you should consider how your solution handles edge cases, such as numbers with zeros, single-digit numbers, and large ranges. Interviewers may also ask follow-up questions about scaling your solution for very large ranges or extending the logic to related problems, such as numbers divisible by their digit sum. Speaking of related problems, you might encounter others that require similar techniques, like LeetCode 202, which focuses on iterative digit manipulation, or LeetCode 258, which involves modular arithmetic with digit properties. These connections can help you build a deeper understanding of problem-solving patterns. When thinking about alternative approaches to this problem, the baseline is a brute force method. This involves checking every number in the given range by iterating through all its digits. While this is simple to implement, it becomes inefficient for larger ranges due to the high number of operations. A more efficient approach is optimized iteration, where you skip numbers containing 0 digits right at the start and exit early as soon as a non-divisible digit is found. This avoids unnecessary checks and significantly improves performance, though it does require slightly more complex logic. For even greater efficiency, you could use pre-computation. This involves generating all self-dividing numbers up to a maximum possible value, like 10,000, and then filtering these pre-computed results for any given range. The trade-off here is that while this method is space-intensive, it allows you to handle multiple queries in constant time. Choosing the right approach depends on the constraints of the problem and the specific requirements of your use case. Great job making it to the end. Today, we explored the concept of self-dividing numbers, discussed key algorithms, and covered their complexities. Remember to practice similar problems for better understanding. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!